Good evening, friend. Settle in and let the day loosen its grip, like a coat slipping from your shoulders. Your chair is steady, the room is warm, and your breath moves in and out like a small, gentle tide. You are safe here. Tonight, we'll follow a quiet question. Where is everything in the universe moving? From the drift of your chest as you breathe, to the slow turning of our planet, to the long glide of galaxies through dark, silky space, there is a soft current beneath it all. We'll let the noise fall away while we trace those currents, unhurried, like starlight crossing a calm lake. If this kind of calm keeps you company, you might like and subscribe, so these night journeys can find their way back to you and to others who need them. For now, close your eyes if you wish, and let's begin to drift. Imagine the night sky above you, quiet, endless, soft as deep water. Every star you see is not still, not even for a heartbeat. Each one drifts, turns, and dances through a universe that never stops moving. The air around you may feel calm, the ground steady beneath your feet, but that stillness is only an illusion. Earth is spinning gently on its axis, carrying you in a wide circle every day. At the same time, it's sailing around the sun at tens of thousands of miles an hour, while the sun itself rushes through the Milky Way like a glowing ember carried on a vast wind. Even our galaxy is being drawn toward unseen shores, mighty regions of gravity whose shapes we can only imagine. Nothing stands still, from the dust that floats in a sunbeam to the clusters of galaxies drifting through cosmic dark. For most of human history, though, it didn't feel that way. The ground seemed firm, the stars eternal, the heavens serene. People looked up and saw the sun rising, crossing the sky and sinking back into night, as if the world itself were the center of all things. Clouds drifted, the moon glowed, and the stars seemed to turn above them, like lanterns hung on invisible strings. It was a comforting thought that we were still while the cosmos revolved around us. That belief took root across the ancient world, in China, in the temples of the Maya, in stories whispered under Greek skies. People imagined a universe that turned around Earth. But it was in the Hellenic world, among scholars who sought order in geometry and logic, that this vision became something grand, a system, not just a story. There, a man named Claudius Ptolemy gathered the wisdom of centuries. He lived in Alexandria nearly 2,000 years ago, when Egypt glowed under Roman rule. A thinker, a mathematician, and an astronomer, Ptolemy wanted to understand the heavens not just by faith or feeling, but by measurement. He collected records of Babylonian star watchers, the sky lore of Egypt, the careful notes of Greek philosophers. From all these fragments, he built a universe, a great clockwork of circles and spheres. He described it in a book later called the Almagest. Inside were pages of numbers, angles, and predictions so precise that the world trusted them for more than 1,000 years. In his vision, Earth rested at the center of a vast crystal onion, each layer turning smoothly around it. The moon nearest, then Mercury, Venus, the sun, and farther still, the slow wanderers Mars, Jupiter, and Saturn. Beyond them all stretched the shell of stars, fixed like tiny fires to a perfect, turning dome. Beyond that, nothing we could know. To him, and to generations after, this was harmony. The circle, the most perfect shape, guided the motion of heaven. The spheres spun in endless music, elegant and divine. And yet, the sky has ways of reminding us that perfection is an illusion. When patient eyes followed the planets, a strange dance appeared. Mars would drift forward, slow, pause, and then move backward. After a while, it would resume its forward path. Jupiter and Saturn performed the same slow loops. The heavens, it seemed, sometimes hesitated. This baffled astronomers. A universe built on simple circles could not explain such behavior. Ptolemy's answer was clever. He imagined smaller circles riding upon larger ones, epicycles upon deferent planets, circling invisible points that themselves circled Earth. It was a celestial ballet of loops within loops, intricate and precise enough to match what the eye could see. Later, he adjusted again, adding a small offset point called the equant, where motion appeared smoother to our sight. With each correction, the model grew more elaborate, more beautiful, more strained, and yet it worked. It gave sailors stars to navigate by. It gave priests and scholars calendars and astrologers their cosmic charts. For 1,000 years, it guided not only ships and harvests, but the imagination of the human soul. It said, "We are at the heart of everything." It said, "The heavens turn for us," but truth, like light, always finds a way through the cracks. By the 15th century, quiet minds began to wonder if the dance might be simpler than all those loops suggested. And in 1543, as Europe turned its gaze toward a wider world, one man dared to whisper a new idea. His name was Nicolaus Copernicus. He was not a king, nor a warrior, but a priest with a patient mind and a habit of looking up. In the still nights of his youth, under the Polish sky, he studied the same stars Ptolemy had once described and found himself unconvinced. The more he measured, the more he sensed a deeper symmetry hidden in their motion. He imagined the sun, not the earth, standing quietly at the center of everything. Around it, the planets drifted like leaves around a slow fire. Earth, he said, was one of them, a traveler, not a throne. Every year, it circled the sun, and every day it spun, giving us the rhythm of night and dawn. Even its axis, he noticed, had a long, slow wobble, a gentle leaning that shifted the seasons across the ages. Copernicus didn't claim this lightly. He studied, calculated, drew diagrams upon diagrams. He built his universe not from faith, but from patient geometry. The closer a planet was to the sun, the faster it appeared to move. The farther away, the slower. His math fit that pattern perfectly, like gears meshing in a hidden mechanism. Still, Copernicus clung to one old idea, that the heavens moved in perfect circles. Because of that, his model, though bold and luminous, could not predict the planets much better than Ptolemy's could. Yet, it carried a quiet, revolutionary grace. It stripped away centuries of complication and placed humanity not at the center, but in motion, part of the grand flow. Imagine what that must have felt like, to learn that we are not the still point of existence, but one note in an infinite song. The Earth itself, this home of ours, drifting and turning through space, while stars wheel and galaxies drift beyond sight. What seemed stable became motion. What seemed ordinary became astonishing. As you breathe now, you move with that motion. You spin with the planet, orbit with the sun, drift with the Milky Way. Even the atoms within you, ancient, restless, echo the same cosmic rhythm. In this great, moving sea, stillness is an illusion, and rest is only the feeling of traveling together. So let the thought settle softly. You are part of the same quiet journey that carries every star, every planet, every grain of dust. The same unseen tide moves through you. Everything is traveling, and everything belongs to that motion. Lift your eyes to the quiet sky. Imagine a slender tube of glass, simple, handmade, turned toward the stars. What began as a toy of curiosity in the hands of Dutch lens makers became, in Galileo's grasp, a window that forever changed how humanity saw itself. Through it, the heavens were no longer smooth and divine, but wild, textured, and full of motion. The first thing he aimed at was the moon. For centuries, it had been imagined as flawless, glowing like a polished pearl. But through the telescope, it revealed another face, craters carved deep as wounds, ridges of mountains catching light, valleys hiding in shadow. The moon was not a perfect sphere, but a world, weathered and solid, as real as the one beneath our feet. Then he turned to Jupiter. 4 small lights hovered nearby. At first, he thought they were stars, but night after night, they shifted places, circling their giant host. Jupiter had its own system, moons orbiting a planet, a miniature cosmos echoing the sun and its family. The old belief cracked. Earth was no longer the center, and Venus, the evening star, offered the final whisper of truth. Galileo watched its light wax and fade through phases, from crescent to full and back again. Such changes could only happen if Venus orbited the sun. Copernicus had been right. Earth, too, was adrift, turning endlessly around the same bright center. But where Galileo gave sight, Johannes Kepler gave form. He inherited a treasury of data from Tycho Brahe, who had spent decades mapping the stars without a telescope, measuring with almost painful precision. Kepler studied those numbers like a monk reading sacred text. He tried to make Mars fit the old rule of perfect circles, but Mars refused. The numbers rebelled. At last, Kepler let go of perfection and listened. The planets, he realized, moved not in circles, but ellipses, stretched loops, with the sun resting at one focus. That became his first law. Every planet travels in an ellipse, not a perfect round. His second law soon followed. A planet sweeps faster when it's close to the sun and slower when it drifts away, yet it always covers equal areas in equal times, a cosmic rhythm of fairness. And then came the third law, the music beneath the dance. The farther a planet lies from the sun, the longer its year. Distance and time were bound together in elegant proportion. Kepler had written the geometry of motion. The heavens were no longer a tangle of guesses, but a measured, graceful system. Yet one great question remained. Why did they move? What invisible hand guided their paths and kept them from flying apart? That answer arrived beneath an apple tree. Isaac Newton watched a fruit fall and saw, in that simple moment, the universe bending toward understanding. The same pull that brought an apple to Earth also tethered the moon in its path, bound Earth to the sun, and guided every planet in its endless fall through space. He named the force gravity, the quiet conversation between every object that has mass. Each body draws another, the strength depending on distance and weight. With this one idea, Newton united heaven and earth. The same rules that shaped a raindrop's fall also governed the stars. His equations revealed Earth racing around the sun at about 30 kilometers per second, swift enough to circle the sun once each year. Mercury, closer to the warmth, sped faster. Mars, farther out, moved more slowly. The pattern was perfect. The nearer a world was to the sun, the faster it needed to move to keep its balance. For the first time, everything obeyed a single set of laws. The sky was not separate from us. It followed the same quiet logic as falling leaves and ocean tides. The universe had become one fabric, woven of both motion and stillness. And still, a deeper motion stirred. The sun, long thought to be the still center, was found to be moving too, gliding around the heart of the Milky Way at more than 800,000 kilometers per hour. Our solar system is not fixed. It's drifting through a galactic tide, orbiting a dark center that hums with the weight of a supermassive black hole. One galactic year, one orbit around that heart, lasts over 200 million of hours. Even that is not the end of the motion. The Milky Way and Andromeda, vast islands of stars, are falling slowly toward each other in a dance that will take billions of years to complete. Together they are drawn by even larger forces, clusters and filaments of matter that stretch like invisible rivers across the cosmic web. Every star, every planet, every atom is caught in that endless drift. Through Galileo's eye, Kepler's patience, and Newton's insight, the story of motion became a story of belonging. We are not the center, but neither are we lost. We are part of a rhythm so vast that its beat moves through our very atoms. The same law that guides galaxies whispers in the fall of rain, the pull of tides, the weight of your body against the chair. Think of it as a kind of music, slow, deep, and everywhere at once. Earth turns beneath you, spinning gently through sunlight and shadow. The sun carries us through the galaxy's spiral arms, past clouds of dust and ancient light. The galaxy itself flows through space like a leaf carried by unseen wind. The stillness you feel is an illusion, a kindness of perspective. Even as you rest, you are moving through the dark with everything else, the stars, the planets, the drifting dust. You are part of the same grand fall, the same curve of motion that has no end and no beginning. Let that thought quiet you. Every breath joins the rhythm. Every heartbeat keeps time with the turning world. The universe is moving, always, and you are moving with it. The night holds you, steady and sure, as gravity hums its soft song through all that exists. For centuries, the sun was seen as a steadfast heart, the unmoving lantern around which everything turned. It burned with quiet certainty, the still center of creation. After the Copernican revolution, the shock of losing Earth's special place eventually gave way to comfort. Humanity found new stability in the sun, the bright anchor holding all the planets in a perfect dance. For a time, that vision felt safe and complete. But the cosmos has a habit of gently undoing what we think we know. The next great revelation would come not from a philosopher or a priest, but from a musician who looked up at night and listened differently. William Herschel, born in 1738 inches Germany, left his homeland to play music in England. Between performances, he fell in love with light, how it bent, how it could be gathered and shaped through glass. He taught himself to grind mirrors and polish lenses, his hands coaxing clarity from darkness. Soon, he built telescopes so precise they rivaled any in Europe. When Herschel turned his instruments toward the sky, he didn't just look, he measured. He counted stars the way a composer counts beats, searching for harmony in the heavens. Night after night, with his sister Caroline by his side, he mapped thin slices of the sky, noting how crowded or empty each region seemed. Slowly, the numbers formed a pattern. The stars were not scattered like dust. They were gathered into a vast, flat structure, a glowing disk. He named it the galactic system. In his sketch, the Milky Way stretched like a great wheel, and at its center, He placed the sun. He could not yet see the farthest stars hidden behind veils of interstellar dust, but his intuition was right. The stars were not infinite in all directions. They belonged to a single structure, bound by gravity and distance. For the first time, humanity understood that we lived inside something larger, a system of stars so immense it defied imagination. Herschel could not have known that the faint clouds of light he sometimes saw, those ghostly smudges he called nebulae, were not clouds at all, but other galaxies entirely, each a separate island universe. Yet even without that truth, his work was revolutionary. He had shown that not only Earth, but even the sun itself, was not at the center of everything. It, too, was merely one bright note in a cosmic symphony. His idea carried a hidden implication. If the stars formed a structure, then the sun had a position within it. And if it had a position, it might also be moving. But how could anyone tell? We observe the universe from a restless platform Earth, which spins on its axis and circles the sun. The sun might be gliding through space as well, yet from our vantage point, all seems still. How, then, can we measure motion when everything moves together? Imagine sitting inside a quiet train. A cup rests in your hand, barely trembling. Through the window, another train slides by. For a moment, it feels as if the other is moving backward. Then you hesitate. Maybe it's your train that's moving forward. Without seeing the ground, you cannot tell. Both views are true. Motion depends on where you stand. It is never absolute, only relative. The universe works the same way. Our sun, our Earth, every star is both moving and still, depending on the frame you choose. That idea fascinated a quiet Dutch astronomer named Jacobus Kapteyn. He was no fiery revolutionary, but a patient craftsman of numbers, a man who preferred long tables of data to grand proclamations. By the late 19th century, scientists already knew that the sun was part of the Milky Way, yet its shape and motion remained uncertain. Kapteyn began gathering stellar data from observatories across the world: South Africa, Argentina, Australia. He studied the tiny, almost invisible drifts of stars across the sky, their proper motions, changes so small they could take decades to detect. Piece by piece, he built a catalog of thousands of stars, their brightness, their direction, their subtle wanderings. When he compared them, a pattern surfaced. The stars did not move at random. They seemed to flow in two great streams, sweeping across the sky in opposite directions. At first, this looked like two vast swarms of stars rotating around different centers, but Kapteyn suspected something simpler and more elegant. He imagined standing in a busy plaza, people walking past from all sides. To your eyes, they appear to move outward, forward, and around you, but much of that motion comes from your own steps. The pattern of motion you see is shaped by your own movement through the crowd. In the same way, the streams of stars could be an illusion, a reflection of the sun's motion through the galaxy. Kapteyn tested this with precise mathematics, and the numbers fell neatly into place. The star's apparent drift only made sense if the sun itself was moving, sailing through the Milky Way, carrying Earth and every planet along with it. He called the direction of that motion the solar apex. By his calculation, we are traveling toward a point in the constellation Hercules, gliding through space at about 20 kilometers each second. Not racing, but drifting an endless, steady voyage through the galactic sea. With that realization, the sun's stillness vanished forever. Our home star was no anchor but a traveler. Everything it held in its gravity, the planets, their moons, their spinning worlds of rock and gas, all journeyed with it through a greater motion. The heliocentric model had turned the universe inside out once before. Now, Kaptein turned it inside out again. The center we thought we'd found had shifted once more. But Kaptein did not stop with motion. He wanted to understand the shape of the Milky Way itself. Using his catalog of star brightness and motion, he built a model of the galaxy, a flattened disk of stars about 40,000 light-years across, with the sun near its center. Today, we know the galaxy is much larger, about 100,000 light-years wide, and that dark clouds of dust had tricked his eye, hiding its true extent. But for his time, his map was astonishing. Kaptein had transformed scattered points of light into a structured universe, a pattern of order in the infinite dark. He had shown that our sun, once the symbol of stillness, was itself in motion, part of a larger tide of stars, flowing through a vast, flattened sea. Think of it, the same sun that rises over fields and oceans each morning is quietly gliding toward Hercules, pulling Earth and everything we know along its invisible wake. The stars above you are not fixed, they are moving companions, bound by gravity's hush and the slow rhythm of the galactic wheel. The night sky is a current, and we are floating within it. And so, what began as a revolution of perspective became something more intimate. Every discovery, Copernicus's shift, Herschel's map, Kaptein's motion has carried us farther from the idea of a center and closer to a deeper truth, that movement is the nature of all things. Nothing holds still, not even the light that reaches your eyes. The universe drifts, and so do we, steady, quiet, carried together through the dark. For centuries, people looked up at the night sky and saw faint, misty patches between the stars' spiral nebulae, they called them. Most believe these were clouds of gas or small clusters within our own Milky Way. But a few wondered if there was something greater, perhaps whole systems of stars, distant and self-contained, floating far beyond our galaxy's edge. That question would change everything we thought we knew about the universe. In 1923, Edwin Hubble turned the Great Hooker telescope on Mount Wilson toward one of those bright smudges, the Andromeda Nebula. Inside its haze, he found a pulsing star known as a Cepheid variable. Years earlier, Henrietta Swan Leavitt had discovered that the rhythm of such stars reveals their true brightness. By comparing that intrinsic light with how faint the star appeared from Earth, Hubble could measure its distance. The result astonished him. The star lay millions of light-years away, far outside the Milky Way. Andromeda wasn't a cloud within our galaxy. It was a galaxy of its own, filled with billions of suns. That discovery reshaped our sense of place. The Milky Way, once believed to be the whole universe, was now just one island in a vast cosmic ocean. Studying other galaxies gave astronomers a way to reflect on our own, to see its structure by comparison. Over time, using radio waves to pierce through dust, they mapped clouds, clusters, and spiral arms. Slowly, the shape of our galaxy emerged, a great rotating disk of stars, curving through space like a luminous whirlpool. Among those who helped chart its motion was the Dutch astronomer Jan Oort. By studying the movements of stars near the Sun, he realized the Milky Way does not spin like a solid wheel. The inner regions move faster than the outer ones, turning it into a graceful swirl. From this, Oort calculated that our Sun lies about 30,000 light-years from the galactic center and races around it at over 200 kilometers per second. At that speed, it takes roughly 225 million years to complete one galactic orbit. Every star we see in the night sky joins us in that immense journey. But what lies at the center? strong enough to hold such motion together? To find out, astronomers turned again to radio telescopes. By mapping the faint 21-centimeter signal emitted by hydrogen gas, they could trace the spiral structure and follow the flow of matter toward the middle. There, near the constellation Sagittarius, they found something strange. Stars moving at incredible speeds around an unseen object. The visible matter wasn't enough to explain their orbits. Something invisible, compact, and immensely heavy had to be there. That hidden mass became known as Sagittarius A*. Later observations revealed it to be a supermassive black hole 4 million times the mass of the Sun, packed into a space smaller than Mercury's orbit. It sits at the heart of our galaxy, quietly anchoring everything that circles around it. Modern radio networks like the Very Long Baseline Array have refined this picture further. 10 enormous antennas, spread across thousands of kilometers, now act as one vast telescope, sharp enough to measure motions in millionths of a degree. By tracking brilliant natural radio sources called masers, tiny beacons from clouds around newborn stars, astronomers have mapped the Milky Way's spiral arms in exquisite detail. The result is a living portrait. Stars flowing in graceful arcs, gas clouds stretching and shearing under gravity, the whole galaxy slowly twisting as it turns. Even so, our home is far from still. The Milky Way ripples like a ribbon of light, its spiral arms rising and falling through space. The region we inhabit, the Orion Spur, drifts gently above and below the galactic plane as the galaxy spins. Beyond that, the Milky Way itself moves through the cosmos, tugged by unseen forces, drawn toward neighboring clusters, part of a still greater dance that stretches across intergalactic space. From Hubble's first glimpse of a pulsing star to the quiet radio whisper of a black hole, our picture of the universe has transformed. We now see ourselves not as the center of anything, but as travelers within a vast spiral, one of hundreds of billions, turning silently in the dark. And through every revolution, every orbit, the same truth remains. We are part of the motion, part of the rhythm, part of the endless song of stars. Light carries stories in color. When something in the cosmos moves toward us, its light waves compress, shifting faintly toward blue. When it moves away, the waves stretch, turning red. These tiny changes, blue shift and red shift, became the universe's own code for motion. In the early 1900s, astronomers began using that code to trace the movements of stars and galaxies. And what they found transformed everything we thought we knew about the sky. Edwin Hubble was one of them. Through careful study, he noticed that nearly every galaxy he measured was slipping away from us, and not just moving, but accelerating. The farther a galaxy lay, the faster it retreated. It was as if the entire universe was stretching, carrying galaxies outward like dots on an inflating balloon. That pattern, so simple and so strange, meant space itself was expanding. The cosmos wasn't static. It was alive with motion, growing from something once impossibly compact. The finding became the foundation of what we now call the Big Bang. But not every neighbor was fleeing. One galaxy, the Great Andromeda Spiral, broke the rule. In 1912, the American astronomer Vesto Melvin Slipher pointed his telescope toward it and saw something unsettling. Instead of red, Andromeda's spectrum leaned blue. It wasn't running away, it was heading straight for us. A century later, with the combined power of the Hubble Space Telescope, the Gaia mission, and the continent-spanning network of radio antennas known as the Very Long Baseline Array, astronomers could finally trace its motion in 3 dimensions. The verdict was clear. Andromeda and the Milky Way are locked in a mutual pull, each galaxy falling toward the other across 2.5 million light-years of empty dark. Even now, the gap between us shrinks at nearly 500 kilometers per second. That sounds cataclysmic, yet cosmic distances turn violence into patience. The collision will not happen for about 4 to 5 billion years, long after our sun has aged into a red giant. And when it comes, it will not look like the explosions that fill our imaginations. Galaxies are vast, but almost empty. The stars within them are so far apart that, even in collision, most will slip past one another unharmed. If a star were the size of a ping-pong ball, its nearest neighbor would sit hundreds of kilometers away. Still, the meeting will not be quiet. Gravity will choreograph a dance of breathtaking scale. The outer arms of both galaxies will stretch into luminous ribbons. Clouds of gas will crash and ignite new generations of stars. Some systems will be hurled outward into intergalactic space, exiled by the tidal chaos. Others will spiral inward toward the merging cores, drawn into the deepening gravity well, where the 2 central black holes will slowly coalesce. The first encounter will be brief, a close pass that begins the slow embrace. Then, for perhaps 2 billion years, both galaxies will circle each other in ever-tightening loops, their shapes twisting and unraveling before finally melding into one. The graceful spirals that define each today will dissolve into a single, massive, oval-shaped galaxy. Astronomers already call it Milkomeda. When that new galaxy forms, it will shine brighter but look softer, its structure smoother, less defined, a golden haze of billions of suns sharing one gravitational heart. If our solar system still endures, it will drift into a new orbit, far from its old home, tracing a gentle path through this merged sea of light. To human eyes, that future lies beyond imagining. But the story is already written in the colors of light reaching our telescopes. The blue shift of Andromeda is a whisper from the future, a promise that even galaxies, across unimaginable distances, are destined to meet. The cosmos, for all its emptiness, is bound by connection. Every red and blue thread of starlight is part of that same woven motion, a slow and endless dance unfolding in the dark. The story of Andromeda and the Milky Way is only a local tale in a far larger epic. Our galaxy is not drifting alone through the dark. It is part of a grander current, a cosmic river of thousands of galaxies, all moving together, drawn by unseen tides across intergalactic space. To understand where we are truly headed, we must step back beyond the Milky Way, beyond the small circle of our local galaxies, and see the larger pattern of gravity sculpting the universe. Our home belongs to a modest family called the Local Group, a cluster of roughly 80 galaxies stretched across 10 million light-years. At its heart stand the 2 giants, the Milky Way and Andromeda, each wrapped in swarms of smaller satellites. Around us drift the Magellanic Clouds, 2 glowing companions, visible from the southern hemisphere. Around Andromeda whirl tiny followers like Messier 32 and Messier 110. These galaxies move together, bound by gravity like siblings in a vast household. But the Local Group itself is only one neighborhood in an enormous cosmic city. Step outward, and you find larger gatherings called galaxy clusters, immense structures where hundreds or even thousands of galaxies orbit a shared gravitational center. Our group belongs to the outskirts of one such cluster, the Virgo cluster, a vast congregation some 65 million light-years away. The entire local group, our Milky Way included, is falling toward Virgo's heart at nearly 600 kilometers per second. And Virgo is not the top of the hierarchy. Beyond it lies something still greater, the Laniakea supercluster, a Hawaiian word meaning immense heaven. It spans more than 500 million light-years and contains about 100,000 galaxies, Virgo among them. Picture a web of light stretching across space, filaments of galaxies flowing along invisible gravitational channels toward dense nodes like Virgo, Hydra Centaurus, and Pavo Indus. Within this web, every galaxy is a bead sliding slowly along the threads of gravity. How do we know this? By watching the universe move. Over decades, astronomers have charted not only the positions of galaxies, but also their motions through space. Red shifts and blue shifts reveal how fast galaxies recede or approach. Yet there is another layer, peculiar velocity, the motion that remains after subtracting the general expansion of the universe. Measuring that sideways drift is delicate work. Astronomers use tools like the Tully-Fisher relation, which links a spiral galaxy's brightness to its rotation speed. Compare how bright it should be to how bright it appears, and its distance emerges. Combine that with its redshift, and you can tell whether it's moving faster or slower than cosmic expansion predicts. These techniques grew into massive surveys like cosmic flows, which mapped the distances and motions of tens of thousands of galaxies. The results were startling. Instead of drifting randomly, galaxies were streaming in the same general direction as if an unseen force were tugging them through space. The flow pointed toward a hidden region beyond the Milky Way's dusty plain, somewhere behind the constellations Centaurus and Norma. Astronomers called this mysterious gravitational center the Great Attractor. In the 1,970 seconds, the first hints of its pull appeared when scientists noticed galaxies sliding sideways at hundreds of kilometers per second. Telescopes couldn't see the source directly because it lay behind the bright clutter of our galaxy's disk, a region aptly named the Zone of Avoidance. But the motion was undeniable. Later, X-ray and infrared observatories peered through the dust and began to uncover the truth. Beneath that veil lay enormous clusters of galaxies, including the massive Norma cluster about 220 million light-years away. As more data arrived, the pattern deepened. The Great Attractor was just one piece of an even vaster entity, the Shapley supercluster, a gravitational titan containing tens of thousands of galaxies. Its immense pool bends the trajectories of entire galaxy clusters, dragging our local group, the Virgo cluster, and the whole of Laniakea toward it. Yet this journey is not a simple fall toward a single destination. Space is more fluid than that, and gravity plays a subtle game. While Shapley's mass draws us one way, another influence shapes our course in the opposite direction, a vast emptiness known as the dipole repeller. Despite its name, the repeller isn't an object at all, but a cosmic void, a region so empty that, in the language of gravity, it pushes rather than pulls. Galaxies tend to drift away from such underdense areas, sliding toward the regions of greater mass nearby. Imagine floating in a slow river. On one side, a waterfall pulls you forward, the Great Attractor. On the other, open, calm water lets you drift away, the dipole repeller. You are not being pushed, but freed from resistance. The result is motion, a graceful drift, shaped by both gravity and emptiness. In 2017, data from Cosmic Flows 3, mapping the movements of more than 18,000 galaxies, confirmed this elegant picture. The universe around us isn't static. Galaxies flow like currents in a cosmic sea, drawn toward the dense regions of the Great Attractor and away from the silent gulf of the dipole repeller. Together, these two gravitational forces, one of presence, one of absence, define the path of our local group through space. If we could see this motion from afar, our galaxies would look like specks of light gliding along invisible streams, flowing toward unseen valleys in the geometry of space-time. The Milky Way, Andromeda, and all our neighboring systems are not fixed points, but travelers, journeying through a landscape shaped by both matter and void. And though we can measure the flow and name the destinations, we remain, like leaves on a cosmic tide, carried forward by a current that began long before we existed and will continue long after our stars have faded. The great threads of the cosmic web are not frozen in space. They drift and sway, carrying clusters and superclusters along invisible currents. Galaxies are not flying through space like ships. They are being carried by the expansion of space itself, like leaves on a rising tide. This quiet stretching of reality is not slowing down. It is accelerating. Every second, the fabric of the universe grows a little wider, the distances between galaxies a little greater. When astronomers measure light from distant galaxies, they find a simple rule. The farther a galaxy is, the faster it seems to recede. But that motion is an illusion of expansion. The galaxies are not speeding through the cosmos. The space between them and between us is stretching, lengthening the very wavelengths of light that reach our eyes. That is why the light shifts toward red, the redshift, a cosmic fingerprint of expansion. This expansion has profound consequences. As space grows, more and more galaxies drift beyond what we can ever see or reach. Their light, stretched endlessly, will fade beyond the limits of detection. One day, their glow will vanish altogether, not because those galaxies have ceased to exist, but because their light will never catch up to us again. They will have crossed the cosmic horizon, the ultimate boundary of visibility. Already, some galaxies lie past that line. The light we receive from them began its journey billions of years ago. With every moment that passes, more will follow. Their starlight, once brilliant, will be pulled into longer wavelengths, first red, then infrared, then radio, and finally, into silence. If we could leap forward billions of years, the universe would look profoundly different. Most galaxies would have disappeared beyond the horizon. Only those bound to us by gravity, the Milky Way, Andromeda, and their smaller companions would remain. Over eons, these survivors will merge into a single enormous galaxy, glowing in the lonely dark. Beyond that family, nothing will remain visible. The universe will appear quiet, calm, and strangely small. Future beings, if any remain, might gaze up and see only one galaxy hanging in a velvet black sky. They may never know that once the heavens teemed with hundreds of billions of others, cosmic history will have folded inward, leaving only local memory, one island of stars adrift in the dark sea. In its youth, the universe was full of collisions. Galaxies crashed together, igniting bursts of star formation and reshaping themselves in brilliant chaos. But as the expansion continues, those encounters will grow rare. The universe will settle. The noise of creation will fade. Eventually, the last new stars will form, burn, and die. The galaxies will dim as their fuel runs out, and the cosmos will cool towards stillness. This slow fading is called the heat death, the final whisper of a universe that has spent its energy and come to rest. The expansion itself does not break the laws of physics. Gravity, thermodynamics, and quantum mechanics continue to rule the stage. Yet the stage itself is stretching beneath them. Some physicists have wondered whether in the deep future, the laws might not remain entirely constant. The universe depends on a handful of numbers, cosmic constants that seem immovable: the speed of light, the strength of gravity, and the fine structure constant, which governs how light and matter interact. These constants are the anchors of existence. The speed of light sets the limit for all motion and communication. The gravitational constant decides how strongly bodies pull one another from planets to galaxies. And the fine structure constant determines how atoms bind, how chemistry unfolds, how stars burn. Even a small change in its value would produce a universe unrecognizable to us, one where atoms might not hold together, where stars never ignite, and where life could not exist at all. So far, every observation suggests these constants remain steady. The universe expands, but its rules hold firm. Yet, a few tantalizing hints suggest that perhaps billions of years ago, the fine structure constant might have been ever so slightly different. If true, it would mean that as space stretches, it could subtly shape the laws that govern it. A universe evolving not only in form, but in its very foundation. Dark energy complicates this mystery further. It is the invisible engine behind acceleration, a force woven into the fabric of space-time itself. We do not yet know what it is or how it behaves. Some theories imagine that dark energy is not constant but dynamic, that as it drives expansion, it could influence the strength of gravity or the passage of time. If that is so, then perhaps time itself is stretching along with space. As galaxies drift apart and light grows fainter, the very rhythm of the universe may be slowing, like a cosmic heartbeat fading into distance. And beyond that, far beyond the reach of imagination, some physicists speak of phase transitions in the deep future. Just as water freezes into ice, the universe itself might one day shift into a new state of being. The laws of physics as we know them could rearrange, replaced by new rules for a new cosmos. Trillions of years from now, the universe we know may vanish, not in flame but in transformation. Stars, constants, even time itself might change their meanings. The cosmos could become something entirely new, another chapter in a story that never truly ends, written in the slow breath of expanding space. At the dawn of the 20th century, scientists pictured the universe as steady and eternal, a grand, unchanging clock that had always ticked and always would. The stars were thought to burn in fixed positions, galaxies to rest in place like jewels sewn into dark velvet. The cosmos, they believed, was calm, balanced, and infinite. Then came the quiet revolution. With new telescopes and clearer skies, a generation of astronomers began to study light with unprecedented precision. Among them was an American named Edwin Hubble, whose patient eyes and relentless curiosity would change everything humanity believed about existence. At Mount Wilson Observatory in California, Hubble worked with the mighty Hooker telescope, the largest in the world at the time, its mirror over 8 feet wide. Through that gleaming glass, he studied faint, misty patches of light that earlier astronomers had called nebulae. No one knew what they really were, perhaps clouds of gas within the Milky Way, or perhaps entire universes of their own. When Hubble analyzed their light, he made a discovery that reshaped the cosmos. Those ghostly smudges were not inside our galaxy at all. There were other galaxies, islands of stars, each containing billions of suns scattered far beyond the Milky Way. In that moment, the universe expanded not just in scale but in imagination. Humanity's home was no longer the universe. It was just one of countless galaxies adrift in an ocean of space. But Hubble's work revealed something even stranger. When he split the light from those galaxies into its rainbow spectrum, he noticed a subtle pattern. The light was shifted toward the red end of the rainbow redshifted. Just as a siren sounds lower when an ambulance speeds away, light waves stretch out when the source moves away from us. The redshift meant that the galaxies were receding. The deeper he looked, the faster they seemed to flee. Every galaxy he studied confirmed the same truth. The universe was expanding. Not a static theater, but a living, growing one. The pattern became known as Hubble's law. The farther a galaxy is, the faster it moves away. At first, this seemed impossible. What force could drive entire galaxies apart? Yet the answer lay not in motion through space, but in the nature of space itself. The galaxies were not racing away like ships on an ocean. The ocean itself was swelling, carrying them outward on its rising tide. Imagine dots drawn on a balloon. As the balloon inflates, every dot moves away from every other, not because the dots crawl across its surface, but because the surface itself stretches. That is how the universe behaves. Galaxies do not soar through a fixed emptiness. The emptiness expands beneath them. This subtle distinction changes everything. Space is not a stage upon which matter moves. It is an actor in the play, alive, flexible, and restless. The galaxies are passengers on that motion, carried outward as the very fabric of reality unfolds. The farther away a galaxy is, the more space stretches between us and it, and so the faster it seems to recede. Some galaxies are now so far that their light, though traveling at the fastest speed nature allows, will never reach us. The expansion of the universe is pulling them away faster than light can bridge the distance. They have already vanished beyond what we call the cosmic horizon, the boundary of the observable universe. Beyond that edge lies a realm forever out of reach, where starlight cannot cross the widening gulf of time and space. The universe we see today, 13.8 billion years after its beginning, is only a small portion of what exists. Beyond our horizon, billions more galaxies drift unseen, their light eternally outpaced by expansion. But within our cosmic neighborhood, gravity still reigns. It binds the Earth to the Sun to the Milky Way, and galaxies to each other. On small scales, gravity overwhelms expansion, holding worlds and clusters together even as the broader universe swells. This strange cosmos has no center, no single point of origin. Every galaxy, from its own perspective, appears to sit in the middle, watching all others recede. It's as if the universe is a balloon that grows everywhere at once, no fixed edge, no privileged place. Stand on any galaxy, and the picture looks the same, an endless scattering of light, each point slipping away into the dark. The idea unsettled early scientists. On Earth, motion is always relative to something fixed, a road, a shoreline, a background that does not move. But in the universe, even the background breathes. The floor of existence stretches beneath everything, carrying us onward without our consent, without even our awareness. And from that quiet realization came the greatest story of all, the Big Bang. The understanding that everything we see once belonged to a single point of unimaginable density and heat. Space itself burst into being and has been expanding ever since, creating time, distance, and the possibility of life. Every beam of starlight, every galaxy drifting outward, still carries the echo of that beginning, a silent record of the universe's first breath. The cosmos is not still. It never was. It is a living tapestry of motion and memory, still unfolding, still becoming. the universe hasn't always expanded at the same steady rhythm. Its pace has changed many times across billions of years, shaped by competing forces that alternately pulled it together and pushed it apart. Right after the Big Bang around 13.8 billion years ago, the cosmos went through an astonishing moment called inflation. In a tiny fraction of a second, space itself ballooned outward faster than imagination can grasp. Galaxies, atoms, even light had not yet formed. Only the raw fabric of space-time was stretching, smooth and vast. Inflation ended almost as suddenly as it began, but the momentum it left behind kept space expanding. After that first burst, gravity stepped in to slow the expansion. For eons, the universe lived in a kind of cosmic balance, a tug-of-war between the outward drive of expansion and the inward pull of gravity. The result was the large-scale structure we see today. Galaxies, strung along filaments, clustered together like dew on a web of invisible dark matter. To describe how fast the universe expands, scientists use a key number called the Hubble constant. It tells us how quickly galaxies move away from one another, depending on their distance. The constant is expressed in kilometers per second per megaparsec, a megaparsec being about 3.26 million light-years. If the Hubble constant is 70 kilometers per second per megaparsec, that means every megaparsec of distance adds another 70 kilometers per second of recession speed. Measuring this constant, however, is one of the trickiest challenges in astronomy. It requires two numbers: how far away a galaxy is and how fast it's moving. To measure distance, astronomers turn to special pulsating stars called Cepheid variables. These stars brighten and dim in a steady rhythm, and their pulse period reveals their true brightness. Compare that intrinsic brightness with how bright they look from Earth, and their distance can be calculated. To find how fast a galaxy is moving, scientists measure its redshift, how much its light has been stretched toward the red end of the spectrum as it moves away. Combine the distance and speed, and you get the Hubble constant. Simple in theory, but maddeningly difficult in practice. Different research teams have gotten slightly different answers, creating what's now known as the Hubble tension, one of modern astronomy's most fascinating puzzles. There are two main methods of measurement, and they don't agree. The first method uses Cepheid variables and supernovae in relatively nearby galaxies. This local approach typically gives a Hubble constant of around 73 kilometers per second per megaparsec. The second method looks at the oldest light in the universe, the cosmic microwave background, or CMB, the faint afterglow left from the Big Bang. By studying the fine ripples in that ancient radiation and running detailed models of cosmic evolution, scientists infer a lower value of about 67 kilometers per second per megaparsec. A difference of just 6 units may sound small, but in cosmology, it's enormous. If both methods are sound, the universe cannot be working exactly as our current theories predict. Somewhere in the equations, something is missing. Maybe the culprit is dark energy, the mysterious force accelerating cosmic expansion. Perhaps it behaves differently over time than we expect. Or maybe there's some unknown form of matter that shaped the early universe and vanished before we could see it. Some theorists even suggest that gravity itself may not be constant on the grandest scales, that Einstein's general relativity might need a subtle revision when stretched across billions of light years. Of course, the issue might not be cosmic at all, but observational. Measuring distances across millions of light years leaves plenty of room for tiny errors that can balloon into big discrepancies. Even the most careful calibration of Cepheid stars, or supernovae, could be off by a fraction that ripples through the results. Likewise, models of the CMB are complex. built on assumptions that may not hold perfectly true. The story grows more intriguing when we consider that the rate of expansion has changed again in recent epochs. In the young universe, when matter was densely packed, gravity reigned and slowed the expansion. But as galaxies drifted apart, gravity weakened, and another force took over dark energy, causing the universe's expansion to speed up once more. This shift occurred roughly 4 billion years ago and continues today. Now, with observatories like the James Webb Space Telescope, astronomers are refining every step of the process, measuring fainter Cepheids, sharper supernovae, and older light than ever before. Each observation brings us a little closer to solving the Hubble tension and uncovering the universe's true rate of growth. When that number is finally pinned down, it will do more than end a scientific debate. It will tell us not just how fast the universe is expanding now, but how it has changed across cosmic time and what its distant future might hold. For in that single value lies the key to the universe's entire biography, its birth, its evolution, and perhaps its ultimate fate. The universe is growing, but not everything within it is drifting apart. That simple fact hides one of the greatest mysteries in science: how gravity, the force that pulls matter together, coexists with the steady stretching of space itself. We know beyond doubt that the universe is expanding. Galaxies are moving farther apart because the fabric of space between them is swelling. Yet, within those galaxies, stars remain bound, planets stay in orbit, and entire clusters of galaxies hold together in great swarms. Why? Because gravity, the invisible architect of order, is strong enough to resist the cosmic pull of expansion on smaller scales. What we see across the cosmos is a vast tug-of-war. On one side, the expansion of space pulls galaxies apart. On the other, gravity pulls them back together. The delicate balance of these two forces has shaped the universe from the beginning. Without gravity's guiding hand, there would be no galaxies, no stars, and no life. Just a drifting mist of atoms spread too thin to ignite or gather. Albert Einstein's theory of general relativity redefined gravity not as a mysterious attraction, but as the curvature of space and time. Anything with mass, an apple, a star, a galaxy, warps the space-time around it, creating a sort of cosmic dip that other objects fall into. The more massive the object, the deeper the dip. This elegant idea explains why planets orbit stars, why galaxies swirl in spirals, and why the universe has structure instead of chaos. Yet Einstein's equations also predict that the universe can expand, and that expansion doesn't tear things apart evenly. The stretching of space acts only over immense distances. On the scale of galaxies or galaxy clusters, gravity's grip is far stronger. Within those regions, space doesn't stretch fast enough to break the bonds of gravity. That's why galaxies stay intact even as the universe grows. Imagine a loaf of bread baking in the oven, dotted with raisins. As the dough rises, the raisins move apart, not because they are crawling away from one another, but because the dough itself is expanding. Galaxies behave like those raisins, carried along by expanding space. But within each raisin, the galaxy itself, atoms, stars, and planets cling tightly together. Our own Milky Way shows how gravity wins locally. Its nearest large neighbor, the Andromeda Galaxy, isn't being pushed away by expansion at all. In fact, the two are rushing toward each other. Their mutual gravity overpowers the cosmic stretching between them, and in about 4 billion years, they'll merge in a graceful collision, forming one enormous galaxy. On slightly larger scales, galaxies gather into clusters, vast cosmic hives containing hundreds or thousands of galaxies bound by gravity. These clusters are among the largest structures the universe can build. Inside them, galaxies orbit one another around a shared center of mass, while the space between clusters continues to expand. Gravity rules within the clusters, but expansion wins in the great voids that separate them. Still, the balance may not last forever. The universe's expansion is accelerating, driven by a mysterious force scientists call dark energy. Unlike gravity, which pulls matter inward, dark energy acts as a push, driving everything apart faster and faster. No one knows what it truly is, perhaps a property of space itself, or an undiscovered field that fills the cosmos. If dark energy continues to strengthen, it could one day overwhelm gravity completely. Some theorists imagine an end called the Big Rip, a final, catastrophic acceleration where galaxies are torn from clusters, stars ripped from galaxies, planets from stars, and eventually, even atoms themselves pulled apart as space expands infinitely. For now, though, gravity still dominates much of the universe. It holds stars in elegant spirals, binds galaxies into shimmering clusters, and weaves the cosmic web that stretches across the observable universe. The ongoing contest between gravity and expansion shapes every pattern of light in the night sky, a quiet reminder that creation and dissolution, attraction and release, are written into the universe's very fabric. The universe is not still. It's a living tapestry that keeps stretching, drifting, and reshaping itself. Across billions of years, gravity has slowly gathered dust, gas, and dark matter into immense cosmic structures, clusters, filaments, and vast empty spaces called voids. These patterns didn't appear suddenly. They were woven by time itself, thread by thread, as gravity pulled matter together into the grand network astronomers now call the cosmic web. Imagine it as a three-dimensional lace of light and shadow, galaxies glowing along filaments like tiny beads on invisible strings, each one linked to others across unimaginable distances. Between these glowing strands lie immense hollows, regions so empty that they could swallow thousands of galaxies and still remain dark. The filaments, both thick with galaxies, are mostly built from dark matter, an unseen substance whose gravity sculpts the universe even though we cannot see it. But gravity isn't the only force shaping this vast design. While it gathers matter into clusters, another influence, the expansion of space, pulls everything apart. Together they create a silent, cosmic struggle. Gravity pulling inward, expansion stretching outward. Over eons, this tug-of-war reshapes everything, widening the gaps between galaxies and thinning the threads that connect them. Inside galaxy clusters, gravity remains strong enough to resist. Hundreds or even thousands of galaxies swirl together, bound by a shared pull, moving like stars in a giant hive. But between clusters, the expansion wins. The voids swell, and filaments stretch thinner and weaker. Astronomers call this slow, unraveling cosmic drift a gentle parting of worlds that were once close neighbors. In the early universe, galaxies collided often, merging in bright, chaotic bursts that forged new stars. Now, those meetings have become rare. The cosmos is growing quieter, more spacious, more solitary. Over time, the empty regions, those vast voids, will continue to grow, making the great web of matter even more fragile. Billions of years from now, the universe may look like a dark ocean scattered with lonely, glowing islands, each a cluster of galaxies, bound together by gravity, surrounded by endless silence. Within those clusters, galaxies will remain companions, but the filaments that once linked them will fade. The light from galaxies drifting away will be stretched by the expanding fabric of space until it slips beyond visibility. This stretching of light, known as redshift, will turn once bright galaxies into ghosts. Eventually, their light will be stretched so far that it becomes undetectable, leaving future astronomers trapped within a small bubble of visible stars, unaware of the vast cosmos that once surrounded them. As the fabric of space keeps expanding, fewer new galaxies will form. In the early days, clouds of gas collapsed easily under gravity to ignite fresh stars. But as matter spreads thinner, gravity loses its grip. Star formation slows, then stops. The universe will keep expanding, but its creative energy will wane. Galaxies will age, stars will fade, and the sky will grow darker. This slow dimming leads to another question, one that touches something deeper than light or matter. If space itself can stretch, could it also change how time flows? Einstein showed that space and time are not separate things, but parts of one fabric, space-time. When mass bends space, time bends with it. Near a massive star or black hole, time runs slower. On Earth, we feel this effect too faintly to notice, but sensitive clocks on satellites tick ever so slightly differently than those on the ground. If gravity can stretch time, what happens when the universe itself stretches? On our small scale, nothing changes. Clocks tick, planets orbit, dawn follows night. But across billions of light years, the expansion of space subtly warps both light and time. As light travels through the stretching universe, its waves grow longer, its rhythm slowing, its color shifting red. The same stretching that turns blue, starlight red, also stretches the unfolding of events. When we watch a supernova explode in a distant galaxy, it doesn't just look faint, it looks slower. Its fiery bloom unfolds in drawn-out motion, like a film played back in slow time. This effect, called cosmic time dilation, means that what happens far away unfolds at a different rhythm than what happens here. The farther the light travels through expanding space, the more its clock seems to lag. And so, when we gaze deep into the universe, we are not only looking across distance, we are peering into the past, into a history stretched and softened by time itself. Some physicists believe this expansion will keep accelerating until even the concept of time begins to fade. They call this distant future the Big Freeze, a universe where every star has burned out, every galaxy grown dark, and all motion has slowed to stillness. In such a universe, time itself might lose meaning. With nothing changing, nothing shining, there would be no heartbeat by which to measure its passing. Time, Einstein taught, is not a single, steady river. It bends, flows, and slows depending on where you stand in the cosmic landscape. Perhaps, as the universe expands towards silence, that river will flatten into a frozen lake, its ripples stilled. Or perhaps, time will remain, flowing invisibly even after light itself has gone. The truth is still hidden in the dark. Scientists continue to wonder whether time is a built-in property of reality or merely an echo of something deeper, an emergent rhythm rising from the dance of matter, energy, and space. If so, then time is not a ruler we hold against the cosmos, it's the music the universe plays as it unfolds. And someday, when the song grows faint, perhaps it will not end abruptly, but fade into a long, soft note that hums quietly through the dark. When we talk about the universe expanding, it's easy to imagine everything, planets, atoms, even the cells in our bodies stretching along with it, but that isn't what happens. The growth of space unfolds mostly in the wide, silent gaps between galaxies. Inside galaxies, stars, planets, and people remain untouched. The forces that hold matter together are far stronger than the slow pull of cosmic expansion. Within each atom, invisible bonds hum with power. The electromagnetic force keeps electrons tethered to their nuclei, while the strong nuclear force holds the nucleus itself in place. That second force is one of the most powerful in nature, hundreds of times stronger than electromagnetism and millions of times stronger than gravity. Because of it, the atoms in your skin, the air around you, and the rock beneath your feet never drift apart. No matter how much the universe stretches, even whole planets and stars resist the expansion. The cosmic tide only becomes noticeable over the vast, empty gulfs between galaxies. Yet the question lingers, could the growing universe still leave a trace in the smallest corners of existence, the quantum realm? At first glance, the answer seems to be no. But quantum physics, the science of the tiniest scales, has a way of revealing surprises. In that invisible world, even empty space is alive. According to quantum theory, the vacuum isn't truly empty. It teems with fleeting particles that flicker into being and vanish again in an instant. These brief flashes of energy, called quantum fluctuations, happen everywhere, all the time. Normally, they're too small to notice, but in the earliest moments of the cosmos, they may have changed everything. About 13.8 billion years ago, the newborn universe went through a burst of unimaginable growth called cosmic inflation. For a fraction of a second, space expanded faster than the speed of light. It didn't break any rules. Nothing moved through space that fast. Instead, space itself stretched that quickly. During that instant, the entire universe ballooned from smaller than an atom to something already vast enough to one day contain galaxies. Here's the astonishing part. Those tiny quantum ripples, microscopic tremors in energy, were stretched along with space. Minute differences in density became great cosmic brushstrokes, the seeds of galaxies, stars, and clusters. The shimmering web of the universe we see today began as whispers in the quantum foam. In that sense, the story of everything of stars, planets, and us may have begun with fluctuations smaller than atoms. The vastness above and the smallness below are bound together in one continuous design. The grand and the minute mirror each other like reflections on the surface of a still pond. Even now, the link between quantum physics and cosmic expansion may continue. Many scientists suspect that dark energy, the mysterious force pushing the universe apart, could arise from the quantum vacuum itself, from the restless sea of particles and energy that never fully disappears. If that's true, the same quantum restlessness that once gave birth to galaxies might now be driving the universe's growth, connecting the smallest vibrations of existence to the largest movements of the cosmos. It's a humbling thought that everything we see, the galaxies wheeling across the night, the light from distant stars, the gravity that binds our feet to Earth, may trace its origin to a moment when space inflated faster than thought, carrying with it the faint fingerprints of quantum noise. In less than a heartbeat, the universe smoothed itself into balance, leaving only the tiniest ripples that would one day bloom into galaxies, stars, and the slow, luminous unfolding of life. Without that instant of wild expansion, the cosmos might have stayed a tangled, chaotic fog, too uneven to form stars or worlds. But because it did expand fast, fierce, and brief, we live in a universe that is vast, graceful, and beautifully structured. Inflation gave space its scale, and in that scale, it left just enough imperfection for creation to begin. After the furious burst of inflation, the universe settled into a calmer rhythm, a slower, steadier expansion that has continued for nearly 14 billion years. For most of that time, scientists believed this growth must eventually ease. Gravity, after all, should act like a cosmic brake, tugging galaxies back together, slowing the outward rush. But at the end of the 20th century, the universe revealed one of its most astonishing secrets. Astronomers studying distant supernovae, brilliant explosions marking the death of massive stars, noticed something strange. These cosmic beacons, so bright they can outshine entire galaxies, are used as standard candles to measure cosmic distance. When researchers compared the brightness of nearby and faraway supernovae, they found that the distant ones were dimmer than expected. That meant they were farther away than the models predicted. The only possible explanation was startling. Instead of slowing down, the universe's expansion was speeding up. It was as if the cosmos had shifted gears and begun accelerating into the void. Something unseen was overpowering gravity, pushing galaxies apart faster and faster. Scientists named this invisible presence dark energy, a force unlike anything else in physics. Today, dark energy is thought to make up nearly 70% of everything in existence. It doesn't gather into stars or galaxies. It doesn't clump or swirl. It seems to be everywhere at once, perfectly smooth and uniform, woven into the very fabric of space. And the strangest part? As the universe expands, dark energy doesn't thin out. It fills the new space as quickly as it appears, keeping its strength constant. Some physicists suspect this mysterious pressure comes from what Einstein once called the cosmological constant, a term he inserted into his equations of general relativity to balance the pull of gravity. At the time, Einstein, like most scientists, believed the universe was static and eternal. His constant was meant to hold everything still. When Edwin Hubble later discovered that the universe was expanding, Einstein dropped the idea and called it his greatest blunder. Yet decades later, when dark energy was found, that abandoned constant returned, suddenly making sense again. If dark energy truly behaves like the cosmological constant, then it may be an intrinsic property of space itself, the quiet hum of the vacuum. Every cubic inch of empty space would contain a whisper of this energy, tiny on its own but overwhelming in total. Even with a density of only a few atoms worth of mass per cubic meter, dark energy dominates the universe simply because there is so much space for it to fill. The implications are immense. If the expansion keeps accelerating, galaxies will drift farther apart until their light fades completely from view. The night sky will grow emptier, colder, lonelier. This is the Big Freeze, a distant future when stars burn out and the universe slips into silence. But there's an even more dramatic possibility, the Big Rip. If dark energy strengthens over time, its repulsive force could one day overpower every bond in nature. Galaxies would unravel, stars would scatter, planets would tear apart, and even atoms would split as the very fabric of space expands faster than anything can resist. For now, though, gravity still holds its ground in many corners of the cosmos. It binds galaxies into clusters, keeps stars circling their galactic centers, and holds us steady on our spinning world. The two forces, gravity and dark energy, shape the destiny of everything. Astronomers continue to chase the nature of this invisible energy. Some theories describe it not as a constant, but as a field, a kind of energy that changes with time and distance. perhaps growing stronger or weaker in different parts of the universe. Others propose that dark energy might interact with gravity in subtle, undiscovered ways, altering the cosmic balance as the ages pass. Whatever it is, dark energy is not a small side note in the story of the cosmos. It is the story's driving rhythm. Nearly 70% of the universe's content is this quiet, invisible pressure. About a quarter is dark matter, the unseen glue holding galaxies together. The bright, ordinary matter of stars, planets, and people, everything we can see makes up barely 5%. The rest is silence and mystery. Perhaps one day, new physics will reveal why dark energy exists and how it began. For now, we can only watch as it carries the galaxies ever outward, stretching space like a slow breath that never ends. The universe expands, and with each passing moment, more of it slips beyond the reach of light. The same cosmos that once rushed from the Big Bang is now being pulled apart by the faintest whisper, a force born of nothing, filling everything, and guiding the future toward an unknown horizon. In the early 1980 seconds, a quiet revolution began to unfold in cosmology. Physicists Alan Guth and Alexei Starobinsky proposed something astonishing. In the first instant after the Big Bang, the universe didn't just expand, it exploded into growth at a rate beyond comprehension. This idea, called cosmic inflation, suggested that space itself ballooned faster than the speed of light for a fraction of a second, smoothing out the newborn universe and setting the pattern for everything that followed. Inflation solved several long-standing puzzles. It explained why the universe looks so uniform on large scales and why galaxies are scattered across space the way they are. Though its driving energy was far more intense than anything we see today, inflation shares a curious kinship with dark energy. Both cause space to stretch. Some physicists wonder if they might be related, perhaps two faces of the same cosmic phenomenon acting at different times in history. By the late 1980 seconds, scientists began building new models to describe how the universe evolved. These relied on cold, dark matter, a slow-moving form of invisible matter that shaped galaxies through its gravity. The models worked well, but didn't match every detail, especially the measured rate of expansion, known as the Hubble constant. Then came a cascade of discoveries that changed everything. In 1992, NASA's COBE satellite detected tiny ripples in the cosmic microwave background, the faint afterglow of the Big Bang. These temperature variations were the imprints of the first structures, the faint blueprint of galaxies yet to form. They confirmed inflation's predictions and forced cosmologists to refine their models of the early universe. A few years later, in 1998, astronomers studying distant supernovae made a shocking discovery. The universe's expansion wasn't slowing down, it was speeding up. That was the birth of dark energy as a real, measurable presence. Follow-up experiments in the early 2000s, such as Boomerang and Maxima, mapped the microwave background in exquisite detail, revealing that the total energy of the universe was just enough to make it flat, neither curved inward nor outward. Yet ordinary matter accounted for only about 30% of what was needed. The rest had to be something else, something invisible. That something was dark energy. The evidence mounted quickly. The 2-degree field galaxy redshift survey in 2001 confirmed that galaxies were spreading in a way that only dark energy could explain. NASA's WMAP satellite, from 2003 to 2010, refined these findings even further. solidifying a model that combined Einstein's cosmological constant with cold, dark matter. This framework, known as lambda cold dark matter, or LCDM, became the gold standard of modern cosmology. In 2013, the Planck spacecraft and the Supernova Legacy Survey tested this model with even greater precision. Their results showed that dark energy behaves almost exactly as Einstein's cosmological constant predicts, varying by less than 10% over billions of years. Later, the Hubble Space Telescope's higher Z team confirmed that dark energy has been shaping the cosmos for at least 9 billion years, long before the current acceleration began. Even so, dark energy remains one of the deepest mysteries in science. It doesn't clump or gather like matter. It doesn't dim, fade, or dilute as space grows. It seems to be an inherent property of the vacuum itself, perfectly smooth and uniform, with a density so small it's almost unthinkable, about 1/10 billion trillion trillionth of a kilogram per cubic meter. Yet, because it fills everything, it dominates the cosmos, accounting for nearly 70% of its total energy. One popular theory ties dark energy to vacuum energy, the restless fluctuations of quantum fields that ripple even in empty space. According to quantum mechanics, particles and antiparticles constantly flicker in and out of existence, borrowing energy from nothing and then giving it back. Einstein's relativity tells us that this vacuum energy should contribute to gravity, effectively adding to the cosmological constant. In theory, it's a perfect explanation for dark energy. But there's a problem, one of the biggest in all of physics. When scientists calculate how much vacuum energy should exist, they get a number so enormous it exceeds observations by a factor of roughly 10 to the power of 120. It's been called the worst theoretical prediction in history. The universe we live in clearly isn't behaving that way, but no one yet knows why. Whatever dark energy is, it seems to exert negative pressure, a kind of gravitational repulsion that pushes space apart. In Einstein's equations, both mass and pressure influence gravity. Ordinary matter pulls, but dark energy pushes, driving the accelerating expansion we observe. If gravity is the universe's anchor, dark energy is the wind lifting its sails. As the universe grows, its contents behave in different ways. Matter, stars, planets, dust thins out as space expands, its density dropping in proportion to the cube of the expansion. Radiation thins even faster because its light waves stretch, losing energy with every passing moment. But dark energy is different. Its density doesn't fade. It stays constant, even as the universe balloons outward. That one simple fact, its unchanging nature, makes dark energy the dominant force in the cosmos. While matter and radiation grow weaker with time, dark energy remains steady, pushing galaxies apart faster and faster. And because of that invisible pressure, the universe is not just expanding, it is accelerating toward a future that may be far stranger and quieter than we can yet imagine. Even though no one has ever directly detected dark energy, the clues pointing to its existence are overwhelming. The most compelling evidence comes from how light travels across the cosmos, its color, its distance, and the quiet message hidden in its stretch. When astronomers measure how the light from faraway galaxies has been redshifted, stretched as space itself expands, they find something astonishing. The universe is growing faster today than it did billions of years ago. Something unseen is driving that acceleration, and we call it dark energy. Another clue comes from geometry itself. The universe, when viewed on a grand scale, appears remarkably flat, neither curving inward like a sphere, nor outward like a saddle. According to Einstein's equations, that balance can only happen if the total energy of the cosmos has a specific value. The matter we can see, plus dark matter, falls far short of that requirement. The missing piece must be something else, an invisible energy woven through space, filling every corner of existence. Patterns in the large-scale structure of the cosmos tell the same story. Galaxies don't scatter randomly. They trace out a vast web of filaments and voids whose spacing reveals how the universe has expanded over time. In the late 1990 seconds, two teams, the High Z Supernova Search Team and the Supernova Cosmology Project, used exploding stars to map that expansion, and what they found changed everything. Type Ia supernovae, which always explode with nearly identical brightness, serve as reliable cosmic yardsticks. By comparing how bright they appear to how much their light is redshifted, astronomers can measure how fast the universe was expanding when that light began its journey. They expected to see signs of the universe slowing down under the pull of gravity. Instead, they discovered the opposite. Galaxies were racing away faster and faster. The universe's growth wasn't breaking, it was accelerating. That revelation earned the two research teams the 2011 Nobel Prize in Physics and cemented dark energy as the leading explanation for cosmic acceleration. Since then, wave after wave of evidence has strengthened the case. Observations of the cosmic microwave background, the faint afterglow of the Big Bang, show slight temperature variations that perfectly fit a universe dominated by dark energy. Studies of gravitational lensing, where light bends around massive objects, reveal the same accelerating trend. Surveys like Wigglesy, which measured over 200,000 galaxies, confirmed that expansion has been speeding up for billions of years. From all this data, a picture emerges. Roughly 68–71% of the universe is dark energy, 27% is dark matter, and less than 5% is ordinary matter, the stars, gas, and dust we can actually see. Even though dark energy's density is almost unbelievably small, around 10 to the power of -27 kilograms per cubic meter, it dominates because it fills every cubic meter of space. Another key clue comes from the integrated Sachs-Wolf effect, a subtle shift in the energy of photons as they pass through massive galaxy clusters or cosmic voids. These tiny temperature changes in the background radiation show that something again, dark energy, is altering how gravity behaves on the largest scales. Despite all this evidence, dark energy remains maddeningly mysterious. It doesn't clump, radiate, or interact with matter, except through gravity. One idea, the simplest and still the most accepted, is that dark energy is an intrinsic property of space itself, a kind of vacuum energy. Even in total emptiness, quantum physics predicts that pairs of particles constantly flicker in and out of existence. According to Einstein's relativity, this restless vacuum should contribute a small but steady energy to the fabric of space-time, a concept represented by the cosmological constant, or the Greek letter L, lambda. This forms the foundation of the LCDM model, the current standard model of cosmology. It elegantly matches the observed shape and expansion of the universe. But there's a catch, a colossal one. When quantum theory is used to calculate how much vacuum energy should exist, the result is around 10 to the power of 120 times larger than what we actually observe. It's the most extreme mismatch between theory and measurement in all of science. If the calculations were right, the universe would have expanded so violently that no stars, galaxies, or atoms could have formed at all. Somehow, almost all of that vacuum energy cancels out, except for a faint remainder that still pushes space apart. No one yet knows why. Something in our understanding of physics is missing, hidden like a single missing note in a symphony that otherwise sounds complete. For now, dark energy remains, the quiet ruler of the cosmos. It doesn't roar or flash, but its invisible hand shapes everything. The speed at which galaxies drift apart, the fate of the stars, and even the long-term destiny of time itself. The universe is accelerating into its future, carried forward by a force that we cannot see but can no longer ignore, a whisper in the dark that has been guiding the cosmos since the beginning. While most scientists describe dark energy as a constant force, the quiet hum of the cosmological constant, others imagine it as something more alive, a field that ebbs and flows across the ages. This evolving form of dark energy is called quintessence. Instead of remaining fixed like Einstein's constant quintessence, behaves more like a fluid energy that can change over time, growing stronger or weaker depending on the era of the cosmos. It doesn't clump into galaxies or stars. It spreads smoothly across space, whispering through the void. In some models, quintessence slows the universe's expansion just slightly compared to what the standard cosmological model predicts. In others, it behaves almost identically to a cosmological constant, subtle, patient, but never truly still. The problem is that no one has yet found definitive evidence for or against it. What fascinates scientists most, though, is timing. Why did dark energy become dominant only now, billions of years after the Big Bang? If it had risen earlier, galaxies might never have formed. The cosmic scaffolding that allowed stars, planets, and life itself to emerge could have been blown apart before it began. This uncanny timing has led some to invoke the anthropic principle, the controversial idea that the universe must have the conditions it does because otherwise we wouldn't be here to observe it. Other models of quintessence include a built-in tracker mechanism, which naturally causes dark energy to become important only at this stage of cosmic history, tied to the density of radiation and matter in the early universe. But there are stranger possibilities still. Some theorists propose a variant called phantom energy, which grows stronger over time instead of staying steady. In this scenario, the expansion of space would accelerate until it overwhelms every form of binding force. Galaxies would drift apart, then stars, then planets, and finally, even atoms would be torn to pieces in a catastrophic finale called the Big Rip. A gentler cousin, K-essence, envisions dark energy made of exotic fields with unusual properties, perhaps even carrying negative kinetic energy, producing bizarre effects on how the universe evolves. These ideas remain speculative, but they reflect a real problem haunting cosmology today: the Hubble tension. This ongoing disagreement between different measurements of the universe's expansion rate suggests something in our understanding is missing. Some scientists believe that a changing form of dark energy, like quintessence, could be the key to resolving it. Others have tried a different approach. Maybe dark energy doesn't exist at all. Maybe Einstein's theory of general relativity needs to be revised. If gravity behaves differently on the largest cosmic scales than it does within galaxies, the universe's acceleration could be explained without invoking dark energy. Yet most modified gravity theories have already run into trouble. In 2017, the detection of gravitational waves and light from the same cosmic collision event, GW 170817, showed that gravitational waves and photons travel at virtually the same speed. That single observation eliminated many versions of these alternative theories, leaving dark energy as the simplest explanation that still fits the data. Astrophysicist Ethan Siegel and others argue that while new theories make bold headlines, none match observations as elegantly as the current model. According to today's best evidence, the universe's acceleration began roughly 5 billion years ago. Before then, gravity powered by matter and dark matter dominated, gradually slowing expansion. But as the cosmos grew larger, matter thinned out, while dark energy remained steady. Eventually, it took control, and the universe began to speed up once again. With every cosmic doubling in size, the density of matter drops to a quarter, an eighth, a 16th, but dark energy stays the same. That imbalance determines our future. If dark energy is truly constant, as the cosmological constant suggests, then the universe will expand forever. Distant galaxies will slip away faster and faster until they move beyond what's called the cosmological event horizon, the boundary beyond which their light can never reach us. Today, that horizon sits roughly 16 billion light-years away. Anything beyond it is already lost to time, its light forever stretched into invisibility. To the astronomers of the far future, only our local group, the merged remains of the Milky Way, Andromeda, and their small companions will remain visible in the night sky. The rest of the universe will fade into black silence. And yet, there are still other endings to consider. If dark energy strengthens, the Big Rip could one day tear the cosmos apart. But if it weakens, the expansion could slow, halt, and then reverse, ending in a big crunch, where everything collapses back into a single, searing point. Some even imagine that collapse sparking a new Big Bang, beginning the cycle again, a universe born, expanded, dissolved, and reborn, forever breathing in and out across eternity. Some scientists imagine a universe that never truly ends, a cosmic rhythm of expansion and collapse, where dark energy might one day reverse its push and pull everything back together. In this vision, the cosmos breathes in cycles, big bangs, followed by big crunches, an eternal pulse of creation and destruction. To understand how such a universe could exist, we must look not only at dark energy, but also at its quiet partner in mystery dark matter. Unlike the matter that makes up stars, planets, and people, dark matter doesn't shine, absorb, or scatter light. It's invisible. We know it exists only because of its gravitational influence. Galaxies spin too fast, galaxy clusters move too wildly, and light bends too sharply around massive regions for visible matter alone to account for it. Something unseen must be adding extra gravity, shaping the cosmic architecture. In the leading model of the universe, the lambda cold dark matter, LCDM model, roughly 5% of the cosmos is normal matter, 27% is dark matter, and about 68% is dark energy. That means almost everything we can touch or see is just a thin layer on top of a much larger invisible foundation. Dark matter alone provides about 85% of all the mass in existence, forming the scaffolding upon which galaxies are built. Despite decades of searching, scientists still don't know what dark matter actually is. It doesn't seem to interact with light or regular atoms, only through gravity. One leading theory suggests it's made of exotic particles called WIMPs, weakly interacting massive particles, or lighter particles known as axions. Another idea proposes that dark matter could be made of primordial black holes, ancient relics from the earliest seconds of the universe. To make sense of its behavior, Researchers classify it as cold, warm, or hot, depending on how fast its particles move. Most evidence points toward cold dark matter, meaning it moves slowly, allowing it to clump together and pull ordinary matter along with it to form galaxies and clusters. Yet not everyone agrees. A few scientists argue that perhaps our understanding of gravity itself is incomplete. Maybe the laws of motion that work so perfectly for planets and stars need adjustment on cosmic scales. This led to alternative ideas, such as modified Newtonian dynamics and other new gravity theories. But none of them explain all the evidence as successfully as dark matter does. Even if gravity does behave differently in some situations, the invisible mass still seems essential to the cosmic picture. The story of dark matter began long before anyone knew its name. In the late 19th century, Lord Kelvin noticed something odd about the stars near our Sunday. He calculated how fast they moved and found that their motions didn't fit the amount of visible mass nearby. There had to be something unseen, what he called invisible matter. Then, in 1906, Henri Poincaré, the French mathematician and physicist, introduced the term matière obscure, dark matter. He suggested that hidden mass might fill space, though he believed it was less abundant than visible stars. By the 1920 seconds, astronomers had gathered more clues. Jacobus Kapteyn in the Netherlands measured stellar motions and found that they seemed influenced by unseen forces. Knut Lundmark in Sweden noticed the same thing: galaxies and stars moved as if something much heavier surrounded them. These early findings hinted that the visible universe was only a small fraction of the whole. Then, in the 1930 seconds, the idea crystallized. Jan Oort, studying the rotation of stars in the Milky Way, concluded that there must be far more mass than the light from stars could explain. Around the same time, the Swiss astrophysicist Fritz Zwicky, working at Caltech, studied the Coma cluster, a vast collection of galaxies. He discovered that the galaxies were moving far too fast to be held together by visible matter alone. To keep the cluster intact, there had to be hundreds of times more mass than what could be seen through telescopes. Zwicky called this missing mass Dunkel Materiae, dark matter. His calculations were imperfect. Astronomy was still a young science, but his insight was revolutionary. He realized that an unseen form of matter must be shaping the cosmos. Zwicky thought it might be ordinary matter that simply didn't emit light, gas, dust, or dim stars. Today, we know that explanation doesn't fit. Dark matter seems to be something entirely different. A kind of mass that slips through light and matter alike, ghostly, yet gravitationally powerful. From Kelvin's first suspicions to Zwicky's bold proposal, the idea of dark matter has grown from a mathematical curiosity into one of the central pillars of modern cosmology. It holds galaxies together, bends light from across the universe, and forms the invisible backbone of everything we see. Yet its true nature, what it's made of, how it came to be, remains one of the most haunting mysteries in science. And as strange as that may sound, dark matter might still be only half the story. For while it pulls the universe together, dark energy pushes it apart. The dance between these two unseen forces, gravity's shadow and the vacuum's breath, continues to shape the fate of the cosmos. The story of dark matter didn't end with Fritz Zwicky's insight. It only began there. Over the following decades, new evidence kept stacking up, reshaping our understanding of the hidden cosmos. In 1939, astronomer Horace Babcock studied the rotation of the Andromeda galaxy and noticed something strange. The stars near its outer edges were orbiting far too fast for the visible matter to hold them in place. According to Newtonian physics, the farther a star is from the center, the slower it should move, just like planets orbiting the Sunday. Yet, Andromeda's outer stars moved almost as quickly as the inner ones. Babcock suspected that dust or absorption effects might be skewing his data, but in reality, he had stumbled upon the signature of dark matter. A year later, Jan Oort found similar clues while studying another galaxy, NGC 3115, and discovered that a massive unseen halo seemed to surround it. His calculations suggested that galaxies are embedded in huge envelopes of invisible mass, a finding decades ahead of its time. Still, the idea of dark matter didn't truly take hold until the 1970 seconds, when multiple discoveries converged. Two separate research groups, one led by Jeremiah Ostraker, Jim Peebles, and Amos Yahill at Princeton, and another by Jan Einasto and his colleagues in Estonia, independently concluded that galaxies must be surrounded by immense halos of unseen matter. At the same time, astronomers Vera Rubin and Kent Ford were measuring the rotation speeds of spiral galaxies using a new type of spectrograph. Their results were stunning. Galaxies did not spin the way they should if all their mass were visible. Instead of slowing down at the edges, their rotation curves stayed flat, clear evidence of something massive lurking beyond the reach of light. Meanwhile, radio astronomers were tracing the faint 21-centimeter signal of hydrogen gas extending far beyond the stars. This neutral hydrogen rotates along with the galaxy, and by measuring it with powerful radio telescopes like those at Green Bank and Jodrell Bank, researchers found that the flat rotation curves continued far into the galactic outskirts. In 1975, Morton Roberts and Robert Whitehurst mapped Andromeda's spin-out to 30 kiloparsecs, nearly 100,000 light-years, and confirmed that the rotation remained flat, even at that distance. This was a turning point. The outer regions of galaxies were clearly dominated by unseen mass, forming vast halos that extended far beyond what any telescope could see. By the late 1970 seconds, most astronomers accepted that dark matter was real. Through the 1980 seconds and 1990 seconds, more evidence poured in. Studies of hundreds of spiral galaxies like the 1996, work by Persic, Cellucci, and Stell, showed consistent dark matter effects across every size and type of galaxy. Observations of gravitational lensing, where light from distant objects bends around massive foreground clusters, revealed that far more mass exists than the visible matter can explain. Measurements of hot gas in clusters, emitting X-rays, also showed gravitational forces too strong to come from normal matter alone. And then there were the delicate ripples in the cosmic microwave background, CMB, the faint afterglow of the Big Bang. These temperature variations, first mapped by NASA's COBE satellite in 1992 and later measured with high precision by WMAP and Planck, matched perfectly with models that include dark matter. Without it, the galaxies and clusters we see today simply wouldn't have had enough time to form. Here's why. In the early universe, radiation dominated. Hot photons scattered constantly off normal matter, keeping it from clumping together. But dark matter, unaffected by light, began collapsing into dense regions first. Its gravity pulled regular matter in after it, creating the seeds of galaxies and the grand cosmic web we see today. Without dark matter's silent scaffolding, the universe would still be a smooth fog of gas, never coalescing into stars or planets. One of the most vivid demonstrations of dark matter's existence is the Bullet Cluster, the aftermath of a massive collision between two galaxy clusters. When they crashed, the visible gas clouds slowed and heated up, glowing brightly in X-rays. But gravitational lensing showed that most of the mass had passed straight through, unaffected. The invisible dark matter moved ahead, while the luminous matter lagged behind, proof that whatever dark matter is, it doesn't interact with light or regular atoms the way ordinary matter does. Dark matter and normal matter may both be forms of mass, but they behave very differently. In the early universe, ordinary matter was electrically charged, tangled with radiation, and constantly interacting with light. Dark matter was immune to this chaos. It influenced the cosmos through gravity alone, leaving a subtle but unmistakable imprint on the CMB anisotropies, the tiny temperature variations that reveal how matter was distributed after the Big Bang. By turning those fluctuations into a graph called the angular power spectrum, scientists can see a series of peaks and troughs. The position and height of each peak reveal key cosmic ingredients: how much matter, dark matter, and dark energy exist in the universe. Experiments like Boomerang, 2000, WMAP, and Planck refined this data to extraordinary precision, confirming the LCDM, lambda cold dark matter, model as the most accurate description of our universe. This model describes how different components of the cosmos evolve as space expands. Matter, whether dark or visible, thins out as the universe grows, its density decreasing with the cube of expansion. Radiation fades even faster, as both its density and energy drop. But dark energy, the cosmological constant, remains steady, filling new space as fast as it forms. Galaxies also obey a quiet but telling rule. The farther you go from the center, the more obvious dark matter becomes. Based on Kepler's laws, the outer stars should slow down, but they don't. They keep circling at nearly the same speed, implying a massive, unseen halo of matter stretching far beyond the galaxy's visible disk. Astronomers confirm this through the virial theorem, which connects the average speed of stars to the total mass of a system. Again and again, the numbers show that galaxies and clusters are far heavier than their starlight suggests. Galaxy clusters, in particular, are laboratories for studying dark matter. Scientists can weigh them in three different ways: by the motion of their galaxies, by the temperature of the hot gas inside, and by gravitational lensing. All three methods agree. About 5 times more mass exists than what can be seen. The conclusion is inescapable. Dark matter dominates the structure of the universe. Gravitational lensing, predicted by Einstein's general relativity, reveals this invisible mass beautifully. When a massive cluster lies between us and a distant galaxy or quasar, it bends the background light into arcs or even full rings. One famous example, Abel 1689, produces elegant curved patterns that trace the cluster's gravity. Even weak lensing, tiny distortions too subtle for the eye, confirms the same result. The distribution of dark matter matches what theory predicts. Step by step, the evidence converges. From galactic rotation curves to the CMB's ancient echoes, from X-ray halos to colliding clusters, every clue points to a universe built on dark matter's hidden framework. It is both the sculptor and the shadow, the quiet architect of galaxies, the unseen weight behind every star. Without it, the universe would have no structure, no galaxies, no life. And yet, for all its influence, dark matter remains utterly invisible and untouchable. The search continues in underground detectors, in space telescopes, and in the cold mathematics of theory. Somewhere, perhaps in the faintest flicker of a particle collision, or in a new signal from the farthest edge of the universe, the nature of this cosmic phantom may finally reveal itself. Until then, it remains the dark half of creation, the silent backbone of the cosmos, holding everything we know in its invisible embrace. Astronomers have long relied on cosmic landmarks to measure the universe's vastness. Among the most reliable are Type Ia supernovae, brilliant explosions that all shine with nearly the same intrinsic brightness. By comparing how bright they appear to how bright they truly are, scientists can gauge their distance, and through them, they discovered something astonishing. The universe isn't just expanding, it's expanding faster and faster. That acceleration is traced to a mysterious pressure in space itself, dark energy. Another cosmic ruler comes from an even older era, baryon, acoustic oscillations, faint ripples that echo through the large-scale structure of the universe. In the early cosmos, before atoms formed, sound waves moved through a hot plasma of light and matter, compressing and rarefying it like ripples on a drum. When the universe cooled enough for atoms to form, those ripples froze in place, leaving a preferred distance between galaxies about 147 million light-years apart. Decades later, galaxy surveys such as the Sloan Digital Sky Survey and the 2-degree field galaxy redshift survey detected that same pattern, just as theorists had predicted. When combined with the cosmic microwave background, CMB, those ripples help fine-tune key numbers, like the rate of expansion and the density of matter, fitting beautifully into the lambda CDM model, the standard map of our universe. But the cosmos isn't expanding evenly everywhere. When astronomers map galaxies in 3 dimensions, they notice subtle distortions. These happen because the redshift, the stretching of light used to infer distance, is influenced not only by cosmic expansion, but also by each galaxy's own peculiar velocity. Superclusters, bound by their own immense gravity, expand more slowly than average. Vast cosmic voids expand faster. This unevenness makes clusters appear slightly squashed along our line of sight, while voids look stretched. It's a small effect, but when averaged over millions of galaxies, it matches the predictions of general relativity. First proposed by Nick Kaiser in 1987 and confirmed by surveys in the early 2000s, these distortions are further proof that gravity and expansion are locked in a delicate dance. Another window into this ancient universe comes from the Lyman Alpha Forest, a dense pattern of absorption lines in the light of distant quasars. Each tiny dip marks a cloud of hydrogen gas, absorbing light at a specific wavelength. When assembled across billions of light years, this forest of lines reveals the web-like structure of matter between galaxies and confirms that our cosmological models are on the right track. Much of that structure depends on the nature of dark matter. Cosmologists describe it as cold, warm, or hot, not by temperature, but by how fast its particles moved in the early universe. The key concept is free streaming length, the distance a particle could travel before the universe's expansion slowed it down. Cosmologists describe dark matter as cold, warm, or hot, not by temperature, but by how fast its particles moved in the early universe. Cold, dark matter moves slowly, which allows small clumps to form first and later merge into larger ones, like galaxies and clusters. Warm, dark matter moves a bit faster, smoothing out some of the smallest structures before galaxies take shape. Hot dark matter, HDM, made of particles such as neutrinos traveling near the speed of light, moves so quickly that it smooths out almost all small variations, preventing galaxies from forming until much later. Observations from deep space surveys show that galaxies formed early, followed by clusters and superclusters, evidence that dark matter is cold. If it were hot, the smallest galaxies would never have taken shape. For a time, some scientists thought dark matter might simply be made of ordinary but hard-to-see objects, planets, dim stars, or black holes, collectively known as MACOs, massive compact halo objects. But gravitational lensing surveys and the elemental ratios predicted by the Big Bang disproved this idea. There simply aren't enough baryons, ordinary matter, to account for all the missing mass. Measurements of the CMB show that only about 4–5% of the universe is made of normal matter, while roughly 30% of its total mass energy must come from all forms of matter combined. That means most of it, about 85% of the matter content, is dark and non-baryonic. So what is it made of? Physicists have proposed several candidates. One of the earliest and most promising ideas involves WIMPs, weakly interacting massive particles. These hypothetical particles would have formed in the early universe and interact through gravity and the weak nuclear force. The so-called WIMP miracle arises because their expected abundance perfectly matches the amount of dark matter observed. Supersymmetry, a theoretical extension of the standard model of particle physics, predicts such stable, heavy particles. For decades, researchers have searched for WIMPs using three main strategies. The first is indirect detection, looking for gamma rays or neutrinos that might be released when WIMPs collide and destroy each other in space. The second is direct detection, where ultra-sensitive detectors buried deep underground wait for the faint recoil of an atomic nucleus struck by a passing WIMP. The third is collider production, in which scientists try to create these elusive particles in high-energy environments, such as the Large Hadron Collider, hoping to glimpse the missing mass of the universe in a flash of subatomic debris. So far, none of these hunts has found a definitive signal, and the silence from supersymmetry experiments has made the simplest WIMP scenarios less convincing. As WIMPs faded from favor, another possibility grew in allure: the axion. First proposed in 1978 by Frank Wilczek and Steven Weinberg to solve a problem in quantum chromodynamics. Axions are almost weightless and barely interact with anything. They could have flooded the early universe and lingered ever since, forming a cold, invisible sea. Axions also elegantly explain some subtle inconsistencies in galactic structure, making them one of today's leading dark matter candidates. The cosmic balance among matter, energy, and radiation also tells a fascinating story about how the universe evolves. As space expands, matter's density decreases with the cube of its size double the universe's scale, and you get 1/8 the density. Radiation thins even faster because its light waves stretch as space grows, losing energy to redshift. But the cosmological constant, thought to represent dark energy, doesn't dilute at all. It stays uniform, exerting a steady pressure that continues to accelerate expansion. This strange difference is why galaxies, supernovae, and the CMB all agree on one story. The universe's structure, formed from tiny fluctuations that grew under gravity, shaped by dark matter, and is now being stretched apart by dark energy. Dark matter pulls, dark energy pushes. Together they choreograph the evolution of everything we see. And within that vast choreography, even the smallest details align. The flat rotation curves of spiral galaxies, the lensing arcs around clusters like Abell 1689, and the temperature ripples in the CMB all echo one another's tale. Most of the universe's matter is invisible, and most of its energy lies in the emptiness itself. It's humbling to realize that everything, every planet, star, and atom we've ever known makes up only the tiniest fraction of the cosmic ledger. The rest is dark, quiet, and patient. Yet from that darkness came order. Galaxies, stars, life, and minds capable of wondering about it all. The search continues in mountain caverns filled with liquid xenon, in satellites tracing faint gamma rays, and in equations stretched to their limits. Somewhere in that invisible sea, the answer waits, carrying the story of how something unseen became the framework of everything we know. The universe, it turns out, is not held together by what shines, but by what doesn't. For decades, physicists have chased the ghostly trail of something that may not even wish to be found. WIMPs, weakly interacting massive particles, remain one of the most enduring mysteries of modern physics. They are invisible, silent, and pass through ordinary matter as if it were mist. Yet their gravity shapes galaxies, bends light, and sculpts the universe's grand design. To confirm their existence, scientists have spent generations inventing ever more delicate ways to listen for the faintest whispers of their presence. The first approach, called indirect detection, searches the cosmos itself for signs of annihilation. If WIMPs collide in space, theory predicts they might destroy each other and release flashes of energy, gamma rays, or neutrinos that observatories could detect. Telescopes like the Fermi Gamma Ray Space Telescope and underground neutrino detectors buried in ice or rock have spent years watching regions rich in dark matter, such as the centers of galaxies and clusters. Occasionally, a faint excess of gamma rays stirs excitement, but none has yet provided unambiguous proof. The cosmos remains quiet, holding its secrets close. The second approach, direct detection, turns its gaze inward rather than outward. Deep underground, far from the noise of cosmic rays, physicists have built chambers of extreme stillness tanks filled with liquid xenon or argon, chilled to cryogenic temperatures. There they wait for a single extraordinary event, a passing WIMP bumping into an atomic nucleus. The recoil would be unimaginably small, releasing just enough energy to light a single photon or shake a few electrons loose. Instruments like Xenon 1T, Lux, Panda X, and the newer Lux Zeppelin experiment have reached astonishing sensitivity, able to detect energy transfers smaller than a snowflake falling on a leaf. Yet, despite their precision, the detectors have so far remained silent. Each experiment pushes the limits further, narrowing the possible hiding places for WIMPs. The third method involves creation rather than observation. In vast circular tunnels beneath Geneva, scientists at the Large Hadron Collider, LHC, smash protons together at nearly the speed of light. In the chaos of those collisions, matter briefly turns into energy and back again, recreating the extreme conditions of the early universe. If WIMPs or other dark particles can be made in these miniature fireballs, their presence would be inferred not from what is seen but from what is missing, energy that vanishes without a trace. The detectors at the LHC record billions of collisions, searching for these invisible footprints. Though tantalizing hints appear from time to time, no clear evidence has yet emerged. The absence of proof, however, has not dampened curiosity. If anything, it has made the mystery deeper, forcing scientists to look beyond the familiar edges of theory. Some researchers have turned toward other possibilities. The supersymmetry framework that first predicted WIMPs, a beautiful mathematical symmetry linking every known particle with a heavier twin, has lost some of its shine after years of null results. The simplest supersymmetric particles have not appeared, leading physicists to wonder if dark matter belongs to an entirely different family of matter. This shift has inspired new searches for lighter, subtler candidates that might interact through unknown forces. Among these candidates, axions have emerged as leading suspects. Unlike WIMPs, axions are feather-light, almost ethereal particles that may have been born in staggering numbers during the first moments after the Big Bang. They were originally proposed to solve a mathematical puzzle in quantum chromodynamics, the theory describing how quarks and gluons bind into protons and neutrons. Yet axions, if they exist, would also fit the dark matter riddle beautifully. Because they move slowly and hardly interact with anything, they would behave like a cosmic mist, filling galaxies and halos without clumping into stars. Detecting them, however, is like trying to hear a whisper in a hurricane. Experiments such as ADMX, Axion Dark Matter experiment, in Washington and Haystack at Yale, use ultra-cooled, resonant cavities and strong magnetic fields to coax axions into transforming into photons. These experiments are tuned like cosmic radios, scanning frequencies where axions might hum. For years, they have listened in silence, though each generation of detectors grows more refined, probing deeper into the dark. If WIMPs and axions are both absent, the universe may be hiding something even stranger. Some theorists suggest sterile neutrinos, hypothetical cousins of the known neutrinos that interact only through gravity. Others propose fuzzy dark matter ultralight particles with wavelengths so vast they blur together, creating gentle waves instead of distinct particles. These ideas challenge not just detectors, but imagination itself. Meanwhile, observations of the cosmos keep giving us indirect proof that dark matter is real. Galaxies spin in ways that visible matter cannot explain. Galaxy clusters bend light far more than their stars account for. The faint afterglow of the Big Bang, the cosmic microwave background, bears subtle patterns that reveal the gravitational fingerprints of invisible mass. In all these clues, dark matter behaves consistently, as though it forms the cosmic skeleton upon which luminous galaxies are hung like lanterns. Still, the silence in our detectors is sobering. It may mean that dark matter is far more elusive than expected, perhaps hiding in realms of physics that lie beyond current understanding. Some scientists now wonder if gravity itself might need revision. Theories like modified Newtonian dynamics and emergent gravity propose that what we call dark matter could instead arise from new laws of motion on cosmic scales. Yet none of these alternatives can explain every observation as elegantly as the dark matter hypothesis. In the laboratories where physicists wait through long, cold nights, a paradox lingers. The universe's missing mass shapes everything from the birth of galaxies to the orbits of stars, yet remains invisible, intangible, almost indifferent to discovery. And still, they listen. Every new null result refines the map of what dark matter is not, narrowing the gap where truth may be hiding. In this way, science moves forward not by what it finds, but by what it rules out. The silence becomes part of the story, the space between stars, the pause between notes. Someday, perhaps, a faint signal will emerge, a flash in a detector, a subtle resonance, a pattern too precise to be coincidence. That moment would change everything. Until then, the search continues, patient, meticulous, and strangely poetic. For in the hunt for the unseen, humanity finds a reflection of its own longing to understand the invisible forces that hold the world together, even when they cannot yet be named. If the universe has taught us anything, it is that even the grandest story can end in silence. For all its bright beginnings, the cosmos may not expand forever. Perhaps gravity, the quiet counterforce that has always pulled back, will one day reclaim its hold. In the early universe, the struggle between expansion and gravity was fierce. Space ballooned outward while matter's own pull tried to rein it in. Many scientists once believed gravity would eventually win. In that vision, dark energy would fade or prove temporary, and the outward rush of galaxies would slow, then stop, then reverse. This scenario is called the Big Crunch, a universe collapsing in on itself. In the crunch, the great cosmic web would begin to tighten. Filaments of galaxies and the immense voids between them would draw together over unimaginable time. The night sky would grow brighter as galaxies collided, merging in a final cosmic blaze. Temperatures would rise until everything, stars, planets, even atoms, was crushed into a single, radiant point. Space and time themselves would fold inward, returning to the state from which they began. It would be a universe reborn through destruction, an ending that mirrors the beginning. But the universe we see does not seem to be slowing down. Every distant galaxy we measure is racing away faster than before. The evidence from redshifts, supernovae, and the faint afterglow of the Big Bang all point in the same direction. Expansion is accelerating, not reversing. Unless dark energy somehow changes its nature, the Big Crunch appears unlikely. Instead, most scientists now expect a gentler, lonelier ending the Big Freeze. In this version, the cosmos does not collapse. It simply stretches until everything drifts beyond reach. The acceleration continues, pushing galaxies farther and farther apart. Eventually, the observable universe will shrink in a different sense, not in size, but in what can still be seen. Distant galaxies will fade over the cosmic horizon, their light stretched into invisibility. To observers living 100 billion years from now, the night sky will look nearly empty. The Milky Way and Andromeda, long since merged into one vast elliptical galaxy, will be an island adrift in an endless dark. Star formation will gradually cease. Stars require cold hydrogen gas to ignite, and that supply will run out. Perhaps 1 trillion years from now, the last generation of new stars will flicker into existence. After that, only the old stars remain, red giants, white dwarfs, and dim embers slowly cooling through the long night. The universe will not end in flame, but in fading. Gravity will still shape the motions of black holes, but even they will slowly evaporate through Hawking radiation, losing mass one quantum at a time. The Big Freeze is not a cataclysm, but a slow unwinding, a long sigh of creation. It is a story where entropy, the steady slide from order into stillness, has the final word. Yet the cosmos offers other possibilities too. Some theories imagine a darker fate, the Big Rip, in which dark energy grows stronger with time. In that scenario, the expansion would accelerate so violently that galaxies, stars, and even atoms would be torn apart. Space itself would stretch faster than light, leaving no connection between one point and another. The universe would end, not in cold silence, but in a final storm of disintegration. Each ending, rip, crunch, or freeze, depends on what dark energy truly is. We can measure its effects, yet its essence remains hidden. If one day someone discovers its true nature, the revelation could rewrite cosmology itself, answering not only how the universe began, but how it must end. For now, our predictions remain stories told from clues in starlight and mathematics, provisional endings drawn from a still open book. In all those imagined futures, one kind of star endures the longest: the humble red dwarf. These faint, cool suns are the universe's slow burners. They live not for billions of years, but for trillions. While massive stars blaze briefly and die in violent bursts, red dwarfs sip their fuel gently, glowing for ages beyond comprehension. In the farthest future, when most galaxies are dark, these tiny red embers will be the final sources of warmth and light. Yet even their patience has a limit. One by one, they too will fade as their hydrogen runs out. The cosmos will enter a new era, the degenerate era, a time ruled not by creation, but by remnants. Dead stars will dominate: white dwarfs, neutron stars, and black holes. Brown dwarfs will cool into invisibility. White dwarfs will shed their last heat, turning into cold, lightless spheres called black dwarfs. Neutron stars so dense that a teaspoon of their matter outweighs a mountain will persist in frozen silence. The universe will be filled with the ashes of its former brilliance. But time marches on. Even the seemingly eternal black holes will not last forever. Through the subtle process known as Hawking radiation, they leak away their mass bit by bit, glowing faintly as they evaporate. A black hole as heavy as our sun would take roughly 10 to the power of 67 years to disappear, a number so vast it defies human scale. By then, the age of the universe today, 13.8 billion years, will seem like a heartbeat at the dawn of time. As the last black holes fade, the universe enters its final act. Space becomes a ghostly sea of scattered particles, lone electrons, positrons, and perhaps a few surviving photons drifting endlessly apart. The temperature drops near absolute zero, not because heat has been turned off, but because there is nothing left to make it. The universe, once vibrant with light and structure, dissolves into perfect stillness. And even matter itself may not endure. Some theories predict that protons, the fundamental building blocks of atoms, will eventually decay, perhaps after 10 to the power of 36 years or more. If this happens, the very fabric of what we call matter will crumble. Every atom, every molecule, every planet and star will dissolve into radiation. What remains will be almost nothing at all, just a thin, fading haze of energy and ghost-like particles. The cosmos will keep expanding, but with no stars, no planets, and no observers, the concept of distance or time will lose its meaning. Physics will still exist, written into the empty geometry of space-time, but there will be no minds left to perceive it. The laws that built galaxies and gave rise to life will persist without witnesses, unread, untouched, yet still real. That may be the final fate of everything, not a grand finale, but an eternal stillness. The universe will not end with a bang, nor even a whisper, but with a slow fading into quiet perfection, a frozen echo of what once was. And somewhere, hidden in that silence, will linger the memory of all that ever burned, dreamed, and wondered under the light of the stars. A silent, endless void. The question of how the universe will end may be the most haunting riddle science has ever asked. Across decades of discovery, physicists and dreamers alike have imagined many endings, some fiery, some frozen, some strangely quiet. Every version begins with the same invisible thread, the expansion of space itself. This stretching fabric of reality dictates everything: the birth of stars, the fate of galaxies, even the final heartbeat of time. Whether the universe keeps expanding, slows, or reverses, all depends on how this cosmic breath unfolds. Beyond the familiar endings, the big freeze and the big rip, lies another possibility: the big crunch, a return to the beginning. In that story, gravity eventually wins the ancient tug-of-war against expansion. If there is enough matter, the pull inward would overpower the outward push, halting the universe's growth. Galaxies would stop drifting apart and begin to fall back together. Over trillions of years, the great cosmic web would tighten. Stars would collide, temperatures would rise, and the sky would grow brilliant again, not from creation, but from collapse. In the final moments, space and time would fold inward until everything, every atom, every photon was crushed into one incandescent point. The universe would end where it began. It's an elegant symmetry, but one the evidence no longer favors. Observations show expansion speeding up, not slowing down. Unless dark energy somehow fades or reverses, a big crunch is unlikely. Instead, the cosmos may be headed for something quieter: the big freeze. This ending is not explosive, but patient, a long unwinding of heat, light, and memory. As dark energy drives galaxies apart, the night sky will empty. Stars will burn out. The Milky Way, merged long ago with Andromeda, will float alone in a vast black sea. In time, the last flicker of starlight will vanish, leaving a universe that glows only faintly with the residual heat of dying worlds. And yet there is another ending, stranger still: the vacuum decay. Quantum physics suggests our universe might not rest in its most stable state. It could be balanced on a knife's edge, a false vacuum, appearing steady but not truly permanent. One day, by pure chance, a tiny bubble of true vacuum might appear. It would expand at the speed of light, rewriting the laws of physics as it swept through space. No warning, no pain, just transformation. Whole galaxies, stars, and atoms would vanish into a new kind of reality. It's a deeply unsettling idea, and entirely possible, though mercifully unlikely anytime soon. Beyond all these scenarios lies the wild idea of the multiverse. Perhaps our universe is only one bubble in a vast cosmic foam, each with its own laws and lifetimes. Black holes might be tunnels between them, birthing new universes as they consume the old. In that vision, even if our cosmos dies, creation never truly stops. It only shifts, blooming again in another domain. Still, the question that glows faintly in all of this is, could life endure? Most scientists favor the big freeze, a future of dimming stars and plunging temperatures. Life, as we know it, depends on heat, light, and energy flow. When the stars fade, how could anything continue? The answer may lie in imagination. Advanced civilizations, if they exist, might learn to feed on different sources. They could draw power from black holes, which release torrents of energy as matter spirals into them. They might capture the last trickles of starlight, or harness the faint hum of background radiation. Life could adapt, slowing its metabolism, stretching each thought and heartbeat across millennia. Just as microbes on Earth thrive in boiling vents and frozen seas, life elsewhere might find a way to survive in the far future's darkness. Eventually, everything will change. The final stars will fade, leaving behind remnants, white dwarfs, neutron stars, and black holes. These relics of creation will rule what physicists call the degenerate era, when no new stars are born and the universe is filled only with leftovers. White dwarfs will cool into black dwarfs, silent and invisible. Neutron stars will persist like ancient monuments of density. Black holes, seemingly eternal, will very slowly evaporate through Hawking radiation, taking tens of trillions of years to disappear. And yet, time will still march forward. The universe will stretch thinner, its temperature sliding toward absolute zero, not because heat has vanished, but because there is nothing left to make it. Particles will drift apart so far they will almost never meet again. Perhaps even protons will decay, erasing the last trace of matter. What remains will be little more than a faint bath of radiation, an echo of all that once was. Some thinkers imagine life could evolve beyond biology, surviving not as flesh but as information, patterns of awareness stored in matter or fields, perhaps even in quantum fluctuations themselves. Such beings might slow their processing to near zero, living on timescales that outlast entire eras of cosmic change. Others dream that life might one day escape this universe entirely, slipping through quantum tunnels or black hole bridges into newborn universes beyond. These ideas border on fantasy, but then again, so did flight, once upon a time. Even before the final darkness, the universe will grow lonely. The expansion of space will push galaxies away faster than light can bridge the gap. One by one, the signals between them will fade. The cosmic conversation will fall silent. Each galactic cluster will become its own island, forever isolated from the rest. No radio wave, no laser pulse, no message, no matter how advanced, can outrun the stretching of space. The last great act of cosmic isolation will be complete. In that far epoch, every civilization that survives will be confined to its own galaxy, its own fragment of eternity. There will be no more sharing of knowledge, no interstellar collaborations. The universe's grand web of connection will unravel thread by thread until only local lights remain. The dream of a cosmos linked by curiosity and communication will fade into myth, and yet, hope is not entirely lost. Within those bound galaxies, those fragile oases of gravity, life and thought may continue for ages upon ages. They could explore, build, and learn, nurturing meaning even in solitude. Perhaps they will carve their stories into the fabric of space, encoding messages in starlight or in the structure of matter itself, signs for no one in particular, but beautiful nonetheless. Or maybe, as the silence deepens, they will turn inward. They will learn to find wonder in what remains, the stars they still have, the memories they still hold. Meaning might no longer come from reaching outward, but from deepening inward, from tending their small garden of existence while the night grows vast around them. The universe does not promise eternity. It offers the chance to marvel. Its story began in fire and will end in silence, yet the time between our time is rich beyond measure. Every equation, every observation, every act of curiosity is a candle lit against the void. Perhaps that is the truest ending of all, not despair, but gratitude. To know we lived in the chapter when the universe was bright and young, when galaxies still spoke across space, when light still carried stories from one shore of infinity to another. The cosmos began with a burst, and now, as it whispers itself towards stillness, we are here to listen. And that, in its quiet way, is enough.